On to our last speaker, not last but not least, of course, Dr. Claudia Hulbert. She is coming to us as a CEO of Geolabe, probably pronouncing that wrong too, a startup dedicated to automated analysis of Earth data, and her research focused on applications in machine learning as a variety of Earth processes. And I'll let her take it from here.
Hi everyone, very happy to be here today. So yeah, I'm the last speaker of the day, so I'm going to try to make this interesting. My name is Claudia Hulbert. So I run a small startup that develops machine learning techniques for geophysical data. I'm a scientist by training. I used to work at the Los Alamos National Lab. I also worked at the OECD for a few years. And so we are developing machine learning methods for a variety of data, focusing mostly on radar and spectral imagery. We have a number of projects monitoring groundwater from space, soil moisture, a few of them with NASA actually, so very grateful. And today I'm going to focus on one particular project and only one, and it's going to resonate a lot with John Goldstein's excellent presentation this morning because it's on monitoring methane using multi-spectral data. So hopefully it's not going to be too redundant. I'm going to try hard on that. So first of all, why look at methane at all? So methane is the second largest contributor to climate change, to warming, basically. It's estimated to account between a fourth and a third of warming to date. It also has a much more potent greenhouse effect compared to CO2, so it's 80 times more potent over a 20-year period, and it stays in the atmosphere for a much less shorter time. So 10 years half-life compared to 100 years half-life for CO2. So basically, if you're able to cut methane emissions today, you're going to have an impact in the short to mid-term. That's why it's widely considered to be one of the fastest ways that we have to slow down warming in the short to mid-term. So there is a lot of push over the past few years to tackle methane. From the corporate side, a lot of voluntary corporate commitments, in particular from energy companies. From the regulation side, so a lot of new regulations being introduced. There's government funding being introduced. So there's been a $20 billion plan announced by the Biden administration last year to tackle methane. There's the European methane strategy. So there's a huge push right now to look at methane. And another specificity of methane emissions is that they tend to be a lot more localized. So there's a very big portion of methane that's emitted by a smaller number of localized leaks. So if you are able to detect these leaks and to fix them, then you can have a significant impact on warming at short time scales. So most of the emissions, they come from, anthropogenic emissions come from either oil and gas, the agriculture sectors, landfills, as well as coal mining, for instance. The current problem is that all existing detection capabilities have a limited quantification completeness. So you can have in situ sensors, or you can have sensors that are deployed on cars or drones or planes. Those are going to have limited coverage, and typically they are also very costly. So there's been a lot of interest over the past few years to look at methane in satellite data, because then you have something that's very scalable, basically. And this is going to be a little redundant, but I'll still talk about it. There's a trade-off that you have to make when you look at methane in satellite imagery. So either you're going to look at what's called hyperspectral satellites, and those are satellites, basically, you look at the reflection of the sunlight on the ground. And some of the satellites are going to have hundreds of colors. This gives you a very good idea of the chemistry, and so you're able to detect methane much more precisely. You need a long exposure time to be able to get this information. So it comes at a cost. Either you're going to have a very small coverage, so you're going to be able to look at smaller areas, and those are going to be target mode satellites. So think of GHGSat or think of Prisma. You have to point those satellites to a smaller area of interest. Or you're going to have very big pixel size. And with those, basically Sentinel-5P, you're going to be able to detect emissions that are very large, typically greater than 25 tons per hour, a small fraction of emissions. So there's been a lot of interest in looking at multi-spectral satellites. Those have the very nice property, and I think a lot of you are familiar with those. They have global coverage. If you look at Sentinel-2, for instance, you have a revisit time between 2 to 5 days anywhere on Earth. So good coverage, very good time resolution. The problem is you have a much less smaller number of colors. The chemical information in there is really poor. And so they have not been built with methane in mind. When you try to detect methane in this type of data, it's extremely noisy. And so basically, current state-of-the-art capabilities are not able to go down more than 2 tons per hour. So you're also able to detect large leaks and a small fraction of emissions, basically. So what we've been doing for the last 2 years now is trying to develop machine learning models that are really tackled to this problem, trying to improve detection capabilities in multispectral data, to be able to leverage the coverage, the time revisit, but to be able to detect the majority of emissions. So we are developing tailored machine learning models, and there's not nearly enough training data to be able to build those models. Like real methane plumes, there's not nearly enough to be able to do that. So we go the synthetic route. We generate synthetic methane plumes using simple Gaussian models. We build very large databases of multispectral data, so in this case, Sentinel-2. We downloaded over 3.6 million kilometers squares of Sentinel-2 data. And in about half of this data, we embed synthetic plumes in a physical, realistic way. Basically, we're going to try to train a model to retrieve those synthetic plumes, and then we're going to test it on real data afterwards. So this way, we have a large data set that's big enough to train robust deep learning models. That's the beast. I'm not going to go into too much details about it. We do develop always our own architectures, so we don't use libraries or things. We build everything from scratch to make sure that they are tailored to this specific problem. In particular, this is a very high-dimensional problem. Your input is the 12 different colors of the spectral band, so a model that's going to be built for RGB data is not going to work on that. So we build our custom architecture. It's an encoder-decoder model. The encoder here is a vision transformer. The decoding is a UNet. And the model is tasked with retrieving basically the extent of the synthetic plumes. I'm happy to talk more about the model itself, but yeah, it's a standard encoder-decoder model, basically. And those are results on synthetics. So I like basically to focus mostly on the images on the lower portion. So if you look at the bottom part here, those are the actual synthetic methane plumes that we embedded in the image, the extent of the plumes. The second to last here, those are the deep learning detections. The third to last, this is the current state of the art. So basically, the current state of the art, it does a very good job at retrieving the larger plumes. When you go to lower signal-to-noise ratio, you don't see anything anymore, whereas our method is still doing a very good job at detecting the emissions. So as I mentioned, we validated on real plumes. We are looking at methane plumes that have been detected by airplane. So this is an open source database published by Carbon Mapper. There's more than 2,000 plumes in that database. We are taking satellite imagery that's close in time to those airborne detections. So of course, they're not at the same time. You wouldn't expect to detect every single one of them. So our detection potential is this number here, the 20%, which represents the average persistence of leaks in that catalog. And what we find is that our model is able to detect robustly most plumes down to 200 kilos per hour. That's over an order of magnitude improvement compared to the current state of the art. After that, the performance declines very sharply. It doesn't mean that we can't detect smaller plumes, but we won't detect the majority of them. And so I can show you a few examples of detections. So you have the map here. That's actually the Carbon Mapper dataset. All those plumes that have been detected by airplane are in red on the map here. And I've just plotted a few examples that correspond to the little black circles. So as I plotted also the catalog leak rate. So you can see that we can go way below the current state of the art of 2 tons per hour. And those come from a variety of sources, which is really nice with this database as well. This is a dairy farm. This is a coal mine. This is a pipeline. There's a couple of natural gas plants, and the rest are oil and gas infrastructure. This is an oil field. So again, you can apply this technique pretty much anywhere on Earth for a variety of different sources. Just a zoom on one of the smallest examples that we are able to detect. on the left, again, the current state of the art. On the right-hand side, the deep learning detections. So currently, at these types of rates, it's only noise, whereas we get actual real detection even from smaller plumes. Now, we can also take this approach, and the nice thing about it is that it's quite versatile. We can apply it to a number of different constellations. So we've been playing around with this a little bit. So you have 3 examples. Those are read leaks, I think, from Algeria, California, and Turkmenistan, respectively. And so we take the model that we trained for Sentinel-2 data, and we apply it with slight modifications to Landsat 8 and the recently launched EMIT satellite, well, low orbit spectrometer, launched by NASA a few months back, just to illustrate the fact that first it's versatile, so you can combine constellations and further improve revisit times, basically. It also enables to automate the detections, because even today in hyperspectral imagery, very often there's going to be someone involved to check the detection by hand. Whereas with this, well, you can just automate it for a number of either multispectral or hyperspectral constellations. So why is it a big deal to move from 2 tons per hour to 200 kilos per hour in terms of detection thresholds? It's because emissions from operations, they tend to follow a Power law. So that's a figure from Jacobs et al. 2022, where he shows basically the distribution of emissions conducted in a number of campaigns, so in California, Colorado, and the Permian Basin. And so basically, you have a lot more methane emitted by smaller leaks. So current detection capabilities in multispectral data that are around 2 tons per hour, that would allow you to detect about 15% of emitted methane. If you're able to go down to 200 kilos per hour robustly, that's more than 85%. So it makes a tremendous improvement in terms of the volume of methane that you're able to detect, basically. So I think I'm even a little bit in advance. To conclude, so yeah, we trained this deep learning model on multispectral data. We built a tailored architecture, and we're able to really drastically improve detection capabilities, which makes this, to our knowledge, like the first methane monitoring system able to detect most emitted methane from operations anywhere on Earth every few days, relying only on existing open source data. So of course, there's further work that we need to be done, like we are planning to merging all those constellations to improve revisit times. There's going to be Sentinel-2C and 2D that are going to be launched next year in 2025, which should bring detection capabilities to about a daily revisit time. And so yeah, as a concluding remark, I just wanted to say there's so much information that's buried in existing like in existing open source data, in existing data sets. And machine learning methods are a tremendous tool to be able to get to that information that sometimes that's the word I'm looking for, escapes the human eye. So yeah, hopefully this is going to be useful. Thank you.